Welcome back to the deep dive. We have a really fascinating tension to explore today. It's one of those clashes that really defines how the modern world is built.
It really is.
On one side, you've got the Silicon Valley mindset. You know the drill. Agile. Move fast and break things.
Right. Push a new update to the App Store every Tuesday at 2 a.m.
Exactly. It's all about speed, iteration, and, fixing bugs after they go live.
Speed is the absolute currency in that world. If you aren't shipping, you're basically dying.
But then you have the world of aerospace. And let me tell you, the motto there is definitely not move fast and break things.
Not even close. It's more like move extremely slowly, check everything 10 times.
And break absolutely nothing, because gravity is very unforgiving.
That's a fair assessment. And for decades, these two worlds, agile software and safety-critical aerospace, they've been looked at as just, oil and water. They don't mix.
You can't exactly A/B test a landing gear system while you're on final approach.
You really can't. But today, we're diving into a research paper that claims they can mix. It's from the University of Porto and CISEC in Portugal.
And the title is From Waterfallish Aerospace Certification onto Agile Certifiable Iterations.
And this isn't just some theoretical think piece. They're attacking the single biggest bottleneck in aviation software: the paperwork.
The dreaded documentation wall.
The documentation wall. They're proposing a very specific strategy to automate the safety certification part, the goal, to let engineers actually code for an airplane using agile sprints.
So iterating quickly, but without getting completely buried under a mountain of manual reports at the very end.
That's the idea.
Okay, so our mission today is to figure out how that works. We're going to break down their strategy, which they call Scrum 4DO178C. A bit of a mouthful, I know.
It is, yeah.
And we'll look at the specific tools they built to make it happen. We're going to walk through the life of a piece of code from just an idea to, certified reality.
It's a game changer, really, for anyone interested in how high-stakes engineering is evolving. It's about how we stop letting the process kill the innovation.
But before we get to the solution, we have to respect the problem. I think most people know that building a plane is hard, but why is the software side so obsessed with documentation? Why can't they just write good code, test it, and call it a day?
It all comes down to the term safety critical. In this industry, a software bug isn't just an annoyance. It's not a spinning beach ball on your laptop.
Boom.
A failure here can result in loss of life, injury, catastrophic environmental damage. Because the stakes are that high, the industry operates on a standard called DO178C.
We're going to hear that name a lot today. DO178C. It sounds like a droid from Star Wars.
But much more intimidating. It's essentially the Bible of avionics software. If you want your code to fly on a commercial aircraft, whether it's the autopilot or the coffee maker,
Even the coffee maker.
you have to strictly follow DO178C. And the central commandment of that Bible is traceability.
Traceability. Okay, let's unpack that. Because in a normal startup, traceability might just mean, I think Steve wrote that code last week. Maybe check his Slack messages.
Right. That's about as formal as it gets in some places. In aerospace, that doesn't fly, literally. Traceability means you need a rigid, unbroken chain of evidence for every single artifact.
Every single one.
It starts with a system requirement. Say, the landing gear must deploy when the lever is pulled. You have to trace that down to the high-level design, then to the low-level requirement.
And it keeps going from there.
But we're just getting started. From the low-level requirements, you trace to the specific source code, the actual C or C++ files. Then you trace that code to the test cases that verify it, and then finally to the test results and who ran them.
So you have to prove that, say, line 402 in the code exists only to satisfy requirement A and that it was tested by test B.
Precisely. And you need to record who wrote it, who reviewed it, and when. If you have a line of code that doesn't trace back to a requirement, that's called dead code.
And that's bad.
It's strictly forbidden. You just cannot have phantom code in an airplane.
And this is where the conflict with Agile comes crashing in, because Agile is all about changing things. You learn as you go, you update requirements mid-sprint.
And that's the nightmare. If you're doing manual traceability, every time you change a requirement, you have to manually update 5 different documents, 3 spreadsheets, and a test plan. The paper calls it a daunting task.
So what usually happens? Do companies just pretend to be Agile?
Kind of. The researchers use the term waterfallish. Teams might code in 2-week sprints to feel modern, but they push all the certification paperwork to the very end of the project.
Oh, so they're just building up this massive technical debt of documentation.
A huge debt.
That sounds incredibly stressful. You finish the software, the plane's ready, and then you spend 6 months staring at spreadsheets trying to remember why you did something a year ago just so the FAA will sign off on it.
It kills innovation because you're terrified to improve the code once the paperwork has started, and it massively slows down time to market.
So, enter the solution. Scrum 4D0178C. Aside from the name, what's the big conceptual shift here?
It's all about breaking the V model.
Okay, visual time. Paint a picture for us. What is the V model?
Okay, so picture a giant letter V. In traditional engineering, you start at the top left with the big system requirements. You work your way down the left side, getting more detailed with design, then coding is at the very bottom point of the V.
And then you climb back up the other side.
Climb up the right side with testing, unit testing, integration testing, system testing, all the way back to the top right.
And that V is the whole project, right? A 2-year, maybe 3-year V?
Exactly. It's one giant cycle. What this paper proposes is what they call micro Vs. Instead of one giant V for the whole plane, you run a tiny, complete V cycle for every single item in your backlog.
So if I'm working on just the fuel gauge display update, I'm doing the requirements, design, code, test, and the documentation for just that gauge, all inside one sprint.
That is the goal. They call it continuous certification. By the time the sprint ends, the paperwork for that specific feature is done. Like really done. Ready for the regulators.
That sounds great for the timeline, but horrible for the engineer. I mean, if I have to fill out compliance forms every 2 weeks, I'm going to quit. I became an engineer to solve problems, not to be a bureaucrat.
And that is the absolute key insight of this paper. You can't do micro Vs manually. The administrative overhead would just crush you.
You have to automate it.
You have to automate the traceability. You need a machine to handle the boring stuff.
Okay, let's talk about that secret sauce. The researchers build a tool chain to do this, and I love that they gave the tools these distinct roles. We have a watchdog and a librarian.
It really helps to think of them that way.
Yeah.
So the first tool is the CMT, the Certification Manager tool. That's your watchdog. It just sits in the background, constantly monitoring your development environment.
So it's watching Jira, it's watching the code repository.
Yes. It's listening for specific events. When a developer moves a task in Jira or makes a pull request in Bitbucket, the watchdog wakes up.
And what does it do?
It grabs the relevant data, who did it, what files changed, what the test results were, and it logs all of it into the traceability matrix automatically.
So the developer doesn't even open a spreadsheet. They just do their work, and the watchdog records the evidence.
Correct. Then you have the second tool, the CPT, the Certification Packager tool, and that's the librarian.
And the librarian's job is to organize all the chaos.
Essentially, at the end of the sprint, or whenever you're ready to release, the librarian takes all those little logs the watchdog collected, gathers the binary files, the test reports, and it bundles them into a potentially certifiable package.
It's like having a robot auditor sitting right next to you.
A helpful one, though. And it's important to note, these tools plug into industry standards. They're not asking engineers to use, like Trello or some generic startup tool. They're integrating with IBM Doors for requirements, Jira for tasks, Bitbucket for code.
And Doxygen for documentation. I want to dig into that for a second. I've used Doxygen before, but usually just to turn code comments into a flimsy PDF manual nobody reads. How are they using it here?
They're using it for the link. It's
Yeah.
actually very clever. Developers use special Doxygen tags right inside the source code comments to reference the requirement ID from Doors.
Oh, okay. So right above the function that lowers the landing gear, I'd put a tag like ref REQ 101.
Exactly. The watchdog scans the code, it finds RDQ 101, and it tells IBM Doors, hey, this C++ file implements this requirement. That closes the loop.
I think I have the concept. We've got micro Vs, and we have the robot team doing the paperwork. But I want to really understand the day-to-day. Let's walk through the actual life of a requirement. The paper breaks this into 4 stages.
Sure. Let's trace a feature from birth to certification.
Stage 1 is specification. So I'm the product owner. I have a new request. Display altitude in feet. What happens?
You create a product backlog item, a PVI, in Jira. But you can't just start coding. In safety-critical work, you have to formally define what that means. So the team does a functional, high-level description analysis.
Which I assume is a bit more rigorous than a sticky note saying fix the altitude thing.
Much more. This definition gets entered into IBM Doors, which is the single source of truth for the project. Then there's a formal review. A checklist is generated to make sure the requirement is unambiguous, verifiable, and safe.
And this is where the watchdog starts working, right?
Right. As soon as that review is marked past, the CMT generates an incremental package. It basically creates a time-stamped proof that says, we defined this requirement, and it was reviewed by these people on this date.
So we haven't written a single line of code, but we already have the first piece of our certification paper trail.
Exactly. So now we move to stage 2, software implementation.
This is where I, the developer, finally get to work. But looking at the process, I'm still not allowed to write code yet.
Not just yet. This is a common misconception about Agile in this space. You don't just hack away. You have to define high-level requirements and low-level requirements first. You have to design the architecture.
So I have to explain how I'm going to code the altitude display before I actually do it.
Yes. And that design document gets reviewed. Only after the design is approved do you finally open your IDE and write the C++ code.
That feels very structured for Agile. It feels, well, a bit like Waterfall.
It is structured, but remember, this is all happening inside one sprint. You're not waiting 6 months for design approval. You're doing it on Monday, it's approved Tuesday, and you're coding on Wednesday. It's just compressed.
Got it. So I write my code, I run a quick test on my laptop, a dry run. It works. Now I want to merge it.
You create a pull request, and this is the critical traceability moment. When you hit Create PR, the watchdog scans your changes. It looks for those Doxygen tags we talked about. It maps the header files, the .h files, to the requirements.
And what if I forgot to tag a requirement? Or if I just wrote some random code because I felt like it?
The system flags it. It'll essentially say, you're introducing code that has no reason to exist according to our requirements, and it won't let you proceed.
Wow. So it stops the technical debt before it even gets into the repository. It forces you to be disciplined.
Exactly. It enforces the discipline automatically. You can't break the rules because the system literally won't accept the commit.
Okay, my code is merged. We move to stage 3, software testing. I'm guessing this is where we go beyond it works on my machine.
Right. The paper distinguishes between unit tests and integration tests, but the key thing here is the environment.
The remote execution.
Yes, until now, you've been running tests on your laptop. But for certification, that's not good enough. When you trigger the testing phase with a pull request, the tests are run on a dedicated, controlled server.
Which ensures a clean environment that matches the final spec.
Precisely. And the watchdog is there again, watching everything. It grabs the unit test report, verifies the results, and bundles it all into the data package. So now our package has the requirement, the design, the code, the review logs, and now the test results, all linked.
Which brings us to the final boss battle, stage 4, HSI and system testing.
HSI stands for hardware and software integration.
This is where things get real. We stop using simulators, and we put the code on the actual flight computer.
Or a very, very close rig, yes. This is the hardening phase.
Yeah.
You're validating that the software plays nice with the electronics, the sensors, the real-world timing. This is the difference between done and done.
And what's our librarian, the CPT, doing here?
This is the librarian's big moment. In the previous stages, the tool was just logging events. But here, the CPT is manually triggered to generate the final certifiable documents.
And these are the big ones.
The really big ones.
Yeah.
It produces the SRD, the software requirement document, and the SCI, the software configuration index.
Let's pause on the SCI, the software configuration index. Why is that document such a big deal?
The SCI is basically the DNA of the software. It lists every single file, every version, every compiler setting, every library used to build that specific release. In the old days, creating an SCI was a nightmare of manual checking.
If you missed one updated library version, the whole thing was invalid.
Exactly. It sounds like trying to list every ingredient in a wedding cake after you've already baked it.
That's a great analogy. And here,
the CPT just spits it out. It knows exactly what's in the build because it watched the whole process. It generates the document in seconds.
that has to be a massive relief for the engineering team. Instead of spending the last 2 weeks of a project formatting Word documents, they just hit a button.
It shifts the focus entirely. The engineers can focus on the content of the work. Is the plane safe? Does the code handle all the edge cases? Rather than the form, did I fill out the table correctly?
So the big question, does this actually work? Or is it just, academic wishful thinking from a university lab?
It's a fair question. But the results section of the paper is really promising. They validated this entire workflow with real aerospace professionals.
So people in the industry.
People with 20-plus years of experience at a major European manufacturer. These are hardened veterans who have seen projects fail.
Okay, and what did they say?
They confirmed that automating the SRD and the SCI is feasible. They took what used to be a traceability matrix nightmare, basically a huge spreadsheet nobody wanted to touch, and turned it into a background process.
Did they mention any downsides? It can't all be sunshine and roses.
There's a catch, and it's a cultural one. The automation relies on strict adherence to the workflow.
Meaning?
If a developer decides to be a cowboy and bypass Jira, or commit code without the Doxygen tags, or skip the formal review,
The automation breaks.
it completely breaks. The watchdog can't trace what it can't see.
So you need the discipline of a pilot, even when you're just writing code. You have to follow the checklist.
Precisely. And the tools are somewhat rigid. This system was built for a very specific stack doors, Jira, Bitbucket. If your company uses different tools, you'd have to rewrite the middleware. It's not plug and play for everyone just yet.
But the proof of concept is there.
Absolutely. It proves the DO 178C compliance, the strictest safety standard we have, does not require a waterfall process. It just requires data discipline, which machines are very, very good at.
This feels like a huge shift in perspective. We usually think of regulation as a blocker, a wall that stops innovation. I can't ship this feature because the FAA won't let me.
That's the common view. But this approach reframes regulation. It treats the rules not as some vague bureaucratic hurdle, but as a set of logic rules. And if it's logic, it can be programmed.
That's a powerful idea. You're literally turning the law into code.
Yes. By baking the regulations into the workflow, into the very tools the developers use every day, you free up the humans to focus on the actual engineering. You're not just checking boxes, you're building a safe plane, and the boxes are checking themselves.
It really brings that micro-V concept to life. Instead of waiting 2 years to find out if your paperwork is wrong, you find out on a Tuesday afternoon.
And that feedback loop is what Agile's all about. It actually makes the product safer. You catch traceability errors instantly while the code is fresh in your mind, not 3 days before an audit when you're totally sleep deprived.
It's incredible stuff. It really makes you wonder what else is out there just waiting for this kind of automation.
That's the question for everyone listening, really.
Here's a thought to leave you with. We just talked about automating the life or death paperwork of a commercial airliner, the strictest, scariest documentation in the world. If they can automate that. Why are so many other industries still drowning in manual reports?
Healthcare, finance, automotive, the list goes on.
Exactly. How many waterfall processes in your own job are just waiting for a micro-V revelation? Are you building the wall, or are you building the robot that smashes right through it?
Something to think about.
Thanks for diving in with us. We'll see you on the next one.